All right, hello and welcome. So this might come as a surprise to some of you, but touchscreens are pretty much ubiquitous these days. Overall, however, touch interaction can be quite boring. The only thing that we can do is, well, touch the screen with a finger. Tangibles are physical objects that we can use as an additional input modality and greatly improve this interactive experience. Tangibles help create many interesting interactions, for example, as game pieces in a tic-tac-toe game for children. We can easily improve the interactive experience on touchscreens with such tangibles. All those systems I have just shown you do not actually work directly on a touchscreen itself, but need some kind of additional sensors, usually cameras. This is because tangibles are typically equipped with small fiducial markers. Fiducial markers are visual markers similar to QR codes that can be tracked by computer vision algorithms. The problem here is that touchscreens do not have a good enough resolution for those algorithms. Capacitive touchscreens have a sensor size of approximately 4 millimeters, which is actually quite large. And this is really unfortunate because commodity tablets are already everywhere, a lot smaller, and we would not have the need to install additional cameras for the tracking. This is where our contribution comes into play. Deep learning super resolution network facilitating fiducial tangibles on capacitive touchscreens. The idea is fairly simple. We have conductive tangibles that are equipped with fiducial markers on the bottom. Those markers generate capacitive images when they touch the touchscreen. Those images have a low resolution due to the core sensor size, and the markers cannot be recognized. The magic happens when we feed those low resolution images into our network, which then generates super resolution images. Detection algorithms can now recognize those super resolution markers, which allows us to create many interesting tangible applications. Usually, guns need data. In our case, we need capacitive images of fiducial markers. For this, we selected 4 different types of fiducial markers that all come with detection algorithms. Since we want to generate super resolution images from low resolution images, we need to collect both low resolution and high resolution data. In our case, the low resolution markers have 30 times 30 pixel and the high resolution markers 60 times 60 pixel. Then we also want to have more than one size of fiducial markers, so our tangibles can also have different sizes. Therefore, we recorded data for 2 conditions, small and large. The small markers have a pixel size of 4 millimeters and the large markers of 6 millimeters. We only used 8 out of the 10 AprilTags 36H11 for training. All other fiducial markers, including the remaining AprilTag 36H11 markers, were used for testing and validation only. This allowed us to create a very generalizable network overall. We used a commodity Samsung tablet with a custom kernel to access the raw sensor data. We also fabricated a custom mount and 76 fiducial markers. Also, we used an OptiTrack to record the rotation of the markers. After some pre-processing and blob detection, we turned the raw sensor data into a dataset of low-resolution, high-resolution image pairs with the same rotation. The low-resolution images are fed into the generator. Our generator consists of blocks of convolutional layers with normalization and activation layers in between. These blocks add their output on top of their input with a skip connection. Residual blocks have been used in the image domain for quite some time due to their generally good performance and low parameter count. Our generator implements 5 such residual blocks. Since this is a super resolution network, the generator also has an upsampling layer that increases the image resolution. For this, we use a pixel shuffler layer that rearranges the depth information of the image into individual pixels. The output is the super resolution image, which is then fed into the discriminator. Overall, the generator has a relatively low number of parameters, and for comparison, the well-known VGG16 has many, many more. Our discriminator uses convolutional layers to decrease the image resolution until only 8 times 8 pixels remain. These indicate the probability of the input being a real high-resolution image or a fake super-resolution image from the generator. Usually, only one value remains to indicate this probability. However, in our case, we use a so-called patch gun that helps reduce the blurriness in these images. Again, our discriminator is fairly small in terms of parameters. What we see here are two examples of fiducial markers, both low resolution on the left and high resolution on the very right. The high resolution is the ground truth, meaning the image we want to approximate. The second column shows the interpolated images with the very good interpolation algorithm Lanczos. The third column, we have our super resolution images. We can see that all image quality metrics have improved, especially the mean absolute error. When it comes to fiducial detection, we see that our network facilitated higher detection accuracies compared to Lanczos interpolation. Here, we also compared the rotation of the detection algorithms with the actual recorded rotation, and again, our network outperforms the Lanczos interpolation. We deployed our network in TensorFlow Lite format on a Samsung Galaxy tablet. TensorFlow Lite shrunk the model down to only 3.8 megabyte and allowed for a fairly fast inference. On a rather old Samsung Galaxy tablet, the network inference took 124 milliseconds, and the entire processing, including detection, about 320. For the deployment, we also 3D printed multi-material tangibles. This is a very interesting technique and allows us to mix conductive materials, here the black parts, with insulating materials. This makes it very easy to fabricate fiducial markers directly into tangibles. Here, we see examples of real-time fiducial interactions. We can use fiducials as input devices for office software to, for example, mark or add comments to texts, or as game pieces in a tower defense game, or as letters in literacy training for children. The literacy training example is quite important. 1 in 5 children is at risk of dyslexia, and tangibles have been shown to greatly increase the learning effect. Apart from that, super resolution fiducial markers could also be used, for instance, to mitigate relay attacks for contactless payments or as authentication tokens for connecting Bluetooth devices in a smart home environment. Thank you very much for your attention.